For question number 32, which are long answer questions of 5 marks each, and relation R on set A is defined as the ordered pairs x plus y is an integer which is divisible by 2. We have to show that it's an equivalence relation. Now, we all know that the relation is an equivalence when it is reflexive, symmetric, and transitive. So our relation is defined from set A to A. So this is a relation is defined from set A to A, and set A has elements -1, 3, -4, -3, 2, -1, 0, 1, 2, 3, 4. Similarly here, -1, -4, 2, 1, 0, 1, 2, 3, and 4. And this is x and this is y. And the relation is defined as this. So our relation is an ordered pair. X belongs to A and Y belongs to A such that X plus Y is an integer divisible by 2. Now we have to check whether it's an equivalence relation, it's an equivalent relation or not. So first of all, let's check it for the reflexive part. So for reflexive part, we have to take the element with the element and check whether this belongs to the relation R or not. Now x plus x, according to the relation, this belongs to the relation R when the sum of these two is an integer divisible by 2. So x plus x is 2x, which obviously is, and because it's even multiplied by 2, so this is an integer divisible by 2. So this implies that x comma x ordered pair belongs to relation R. Therefore, this relation is reflexive. So this relation is reflexive. Now let's check the symmetric part. So for symmetric, let's consider that x comma y belongs to R, and if you have proved that y comma x belongs to R, then it is symmetric. So x comma y belongs to R, that means x plus y is an integer divisible by 2. So x plus y is an integer divisible by 2 means that y plus x is also an integer divisible by 2. If y plus x is an integer divisible by 2, that means y plus x belongs to relation R. And if y plus x belongs to relation R, that means R is symmetric. So this is symmetric. And let's check whether it's transitive or not. So for transitive, let's say we have x comma y belongs to R and y comma z belongs to R. And if we are able to prove that x comma z belongs to R, then it's transitive. So this gives that x plus y is an integer divisible by 2, and this gives us y plus z. So this is an integer divisible by 2, and y plus z is also an integer divisible by 2. So if this is an integer divisible by 2, this is an integer divisible by 2, that means their sum x plus y, this implies x plus y plus z is also an integer divisible by 2, which gives x plus 2y plus z is an integer divisible by 2. So this is divisible by 2, that means x plus z is also, so this implies that x plus z is an integer divisible by 2, which means x comma z is in relation, and if x over z is in relation, that means R is transitive. Now we have shown that R is reflexive, symmetric, and transitive. So this implies that R is an equivalence relation. Okay, if R is an equivalence relation, so next is to find the equivalence class for set. So we have to find all the elements which when added to 2 gives us an integer which is divisible by 2. So that would be minus 4, 2 minus 4, 2 plus negative 4 is negative 2, which is divisible by 2. Then it's negative 2 and 0 and then 2 and then 4. So this is equivalence class for the set. So which is negative 4, negative 2, 0 to 4, negative 4, negative 2, and 0 to 4. This is the equivalence class. Okay, for question number 33.